Okay, we want to talk about partial derivatives. We want to talk about them rigorously. We want to talk about them from the definition. We've seen how to use them. We've seen what they mean. But we got to get to the definition because a lot of times you need to understand things at the basis of the definition. So if we've got one of our truncated prisms, this one is truncated by something that's a little bit curvy, okay? So we've got a truncated prism here. And x direction's this way, y direction's this way, and we want to talk about the partial derivative with respect to y. So, as you know, we hold x constant and we let y vary. Well, x is constant between this point and this point of the plane, right? And between every point in the plane that intersects this surface. So, here's our point xy. Here's the point x y plus delta y. Right, x is the same here. This is xy, so we got some delta y across here. Then we got some average slope here, which represents the average rate of change of the value of f with respect to y. It's y that's changing, and that makes f change. X is being held constant, okay? Now if we look closely at this thing, we see that, let's get an angle. Got to coordinate myself with this camera, but if you look at it closely, there's some curvature here, okay? So what we're getting between here and here is an average rate of change of y, of f, or z if you want, with respect to y, right? Now we want the instantaneous rate of change, which is the actual slope of the tangent line at this point. You're very familiar with that and how we use it. Okay? So what do? Well, we do the same thing that we do in first year calculus. Okay, well, here it is on the board. You know, we got the f of xy here and the f of xy plus delta y here and the delta y here, right? Now, this is written kind of badly because I kind of squeezed it in. It said slope is the average rate of change of f with respect to y. Okay? If we want the instantaneous rate of change, we take the limit as delta y approaches 0 of f of x y plus delta y minus f of xy divided by delta y. And that just shrinks the delta y interval down the same way it's done in first year calculus. You know, if you got a curvature here, then the average slope is this, the average rate of change, right? Because it goes from this point to this point, but the instantaneous rate of change is this. And we know how that works. Okay, we know those pictures, I hope, from first semester calculus, from first year, well, actually first semester and first year. Okay, from calculus 1. Okay, well, there's our definition. Well, let's just apply the definition. Let's apply the definition to our favorite function. What's our favorite function?
2 square roots of xy?
Yes. Okay. So if f of xy equals 2 square root of xy, then the limit as delta y goes to 0 of f of x plus f of x y plus delta y minus f of x y over delta y equals the limit as delta y goes to 0 of 2 times the square root of x times y plus delta y minus 2 times the square root of xy. All that divided by delta y. And we algebraically simplify this. First of all, we have a common factor, 2 square root of x. It has nothing to do with y or delta y, right? It has nothing to do with delta y. Okay? So we can factor that out. And we get this, right? And then what do? Well, Elam, you actually came up with in class the other day. We kind of multiply by a conjugate of this thing, right? Numerator and denominator. And I'm not going to do that. That's standard first year calculus. Review it if you need to. Okay? But what we're going to get in the numerator is delta y. In the denominator, we're going to get you know, and I'm doing my algebra in my head, not doing it right. Probably should have left myself more room, but we're going to have square root of y plus delta y plus the square root of y. Okay, that's still the limit, and I forgot to write that in, right? And we still have the delta y down here, and I'm messing this up. So I'm going to stop a minute and fix it, and then we'll go on. It's very simple. If you write out every step and don't try to do things in your head this time of the morning, okay? Yeah, so we'll fix that in a second.